It is what it is. What? Go away. Shh. Okay, so Taylor series. Okay, so basically, like, how is this different than power series, right? Like, what's really the difference? What's going on? So when we talked about power series, we actually started with the series, right? So when talking about power series, we started with a series, right? Then we defined a function on its radius of convergence. So we know that there's a thing called this radius of convergence, which told us that it converged absolutely, for any x within that radius of convergence. And we could use that to define a function. And then we talked about properties of that function. And defined a function, right? And we learned that it was differentiable. We learned that it was integrable. We learned that when you differentiated it, you could just differentiate power series term by term. Same thing when you integrated it. It was continuous, yada, yada, yada. And one of the things I mentioned there actually is that the function is, if you define a function using its power series, it effectively has to be infinitely differentiable, precisely because of this fact that, it's differentiable, and its power series is the differentiated power series. And then you can go to it and bootstrap it again, right? Like that thing is differentiable with the same radius of convergence. And so you can just continue to, sort of make your way down. So actually it was C infinity, right? So with Taylor series, we actually want to go the other way. All right, hold on. Cat's being loud and annoying. I'm going to go fix that. All right, fixed. So with Taylor series, we're going to go the opposite direction. So with Taylor series, what we're going to do is we're going to start with a function, and we're going to see, can we write down some sort of power series representation for it, which, agrees with it. So for Taylor series, we start with a function and try to find a power series representation. Okay, so there might be a couple things that you forget about Taylor polynomials, because that's sort of where we need to start, right? The Taylor polynomials are in some sense going to be like a good first approximation. Hopefully they're going to represent, the partial sums of the series that we get to, but let's just remind ourselves very quickly what the Taylor series is and what the Taylor remainder theorem is. So recall, so if f is Cn, right? So n times continuously differentiable. Really, we just need n times differentiable, but let's just take Cn. Then the Taylor polynomial for f at A is, I think I was calling it PNA. X minus A to the K, like so, right? That thing is pretty close to a power series, right? In the sense that it is, it's finite. It's not an infinite series. It's just a polynomial. But you can imagine if we took n off to infinity, that thing is a power series, right? But just because it's a power series doesn't mean that, again, that thing has a non-trivial radius of convergence. And if it has a non-trivial radius of convergence, doesn't mean that it actually agrees with the polynomial. So in order to be able to do something about that, we need to, again, recall the Taylor remainder theorem. And the Taylor remainder theorem goes like this. It might be I'm pretty like, I'm not going to state it verbatim how I did it before, but the same hypotheses. So this is the Taylor remainder theorem. And we proved this way back in like November. And it said if F is type Cn plus 1 on an interval I, and Rna, right? This was the Taylor remainder, is F minus Pna for some A and I. Then there exists some C in I such that Rna of x is f to the n plus 1 of c divided by n plus 1 factorial x minus a to the n plus 1, right? And again, this is pretty easy to remember. That more or less looks like the next term in the Taylor, like that would be the next term of the Taylor polynomial, except instead of f, the n plus first derivative of f at the point A, we have to take it at some point C, right? And that's why we get equality instead of just, the next term in the approximation. We actually get equality if we're willing to use the C. And again, it screams mean value theorem, and we did sort of prove this more generalized version of the mean value theorem in order to be able to do this, but this is the Taylor remainder theorem. And when we did integration by parts, one of the assignments I gave you was to basically prove this theorem, but with an integral remainder, right? Hopefully you remember that. And you can actually use that theorem to prove this one as well. So if you wanted to do that, you could. But we have this theorem. Now, the great thing about this theorem is it effectively says that our approximations get better and better and better as, right, like this remainder is getting smaller and smaller and smaller as n becomes very, very large, right? So effectively, I'm just going to call it the TRT for now, because I don't want to write that out the whole time, right? The Taylor remainder theorem. The TRT says taking higher order approximations generally leads to better approximations. And obviously, your point X has to, if your point X is closer to A, it gives you better approximations. So the TRT says 1, taking n large generally leads to B large. Generally leads to better approximations. That really, you kind of can. I'm going to show you an example where you can get into a little bit of trouble, but yes, effectively, that's what we're going to do. Now, one of the small problems with that is that when you take the limit as n goes to infinity, that c here depends on n, right? So we sort of fixed f being type Cn plus 1 at the beginning. So c here depends on n. So as we take a limit as n goes to infinity, we have to be a little bit tricky there to ensure that we're not, doing something funky with those c's. So for example, if this interval I here is all of the real numbers, and that c now, as we go to infinity, maybe that c also goes to infinity, and then f becomes unbounded, like maybe it grows exponentially as we do that or something, right? Some trickiness there can happen. If we restrict ourselves to, if our derivative is bounded and our function is, x is really close to a, we can say some stuff, but sort of it's hard to just go straight to taking a limit as n goes to infinity. We need to know a little bit more about the function. We need to know a little bit more about the interval before we can do that, but we'll do some examples. So this leads to better approximations. Generally, right, again, it sort of depends on the function itself. And the thing that this generally comes from, this, we know this because of the n plus 1 factorial in the denominator. N plus 1 factorial grows really quick. Now, in theory, I could give you a function which grows faster, right? And its derivatives grow faster. So we have to be careful about that. But generally, that n plus 1 factorial is going to beat most things. And 2, the closer x is to a, the better the approximation, right? X is to a, the better the approximation, right? Because you got this x minus a to the power of n plus 1 term here. If that's big, potentially you could be in a lot of trouble. Okay, so that's sort of the thing that we have to keep in mind here. So now a very natural question to ask is, does the Taylor series, if you let n go to infinity, so if f is c infinity, maybe we should just write this down. It's a question. So if f is c infinity, let's say on some interval I, right? So it's infinitely differentiable. You can differentiate it as many times as you want. All of its derivatives are continuous, the whole shebang, so that you can take a Taylor polynomial to arbitrary degree. And we let n be infinity, right? Like we take the Taylor series, right? We take the infinite Taylor polynomial. Okay, which we're going to call the Taylor series. Does f of x equal its Taylor series? Right, this is the question. So again, this is a really subtle point. So let's think about it. I've got a function. I can use that function to define a series, but do I know that that series actually agrees with the function, right? We've tried to make sure that it does. If you go back and you remember when we were first talking about Taylor polynomials, we defined Taylor polynomials in such a way that they would be good approximations, right? That was our goal when we did that. But just because it's a good approximation doesn't mean it actually works, right? Do you know what I mean? Like it could turn out, especially if x is very, very big, or far away from our centering point A, that this might not be true, right? F of x might not be equal to the value of this series. So we've got a definition here, and then I'll give you an explicit example. So definition. So a function is said to be analytic if it converges. And it does equal the value of its thing. So let me just see where I put that, blah, blah, blah. Okay, I don't remember where I put it. So if I subset R is an interval, and f is a C infinity function from I to R, is C infinity, then f is analytic at the point A if there exists some delta greater than 0 such that f of x is equal to its Taylor series. If x minus a is less than delta. Okay, and then it's analytic on I if it's analytic at every point in I, right? We just say f is analytic if it is analytic at every point in its domain. Okay, so this is what it means to be analytic. It means, yeah, you agree with your Taylor series on some non-trivial, interval around every single point. And analytic functions, I mean, like, what are we doing? This is a course called analysis, right? That's what analysis really is to some extent. It's the study of analytic functions. I mean, loosely speaking, but, analytic, we spent so much of the course to get to this point is sort of the last definition we're going to do, but this is what it means. This is what it means for a function to be analytic. Now, there's going to be weird things. Okay, and I'm going to give you an example in a second here, but just as a heads up, if you take complex analysis is all about analyticity. It's the only thing you care about. And a whole bunch of those weird, crazy theorems you guys know, that again, that I hate, that are on YouTube, like the sum of all the positive numbers is like -12th or whatever. Those things are all analytic continuations where like you have a function and it's not defined somewhere, it's not analytic. So what you do is you manipulate it and you massage it in such a way that it becomes analytic somewhere, right? And this is what allows you to do these sort of weird, nonsensical things. You've extended a function in an analytic way. Another note here is that when you go and you take complex analysis for complicated reasons, they use completely different words in complex analysis. Okay, so I don't necessarily expect you to remember this now, but one of the things you'll learn when you learn complex analysis, and again, everything. So, okay, let's just do it. So there's the word differentiable, and you already know what that means, right? You know what a differentiable function is. There's the word analytic. Now you know what the word analytic means. There's also the word holomorphic. Okay, so and this is the word sort of everyone still uses for complex functions. We use the word holomorphic. Now, holomorphic and analytic and differentiable are all the same thing. Okay, in complex analysis. And historically, the thing is when complex analysis was first being invented, we didn't know that that was true. Holomorphic means, like, I actually think I'm sufficiently removed from historical context that I don't remember which thing holomorphic was, but I'm pretty sure holomorphic was basically complex differentiable, right? And then there's analytic. And then you can prove that if you're differentiable, again, remember I've sort of mentioned that in complex analysis, if you're once differentiable, you're actually infinitely differentiable, right? So in complex analysis, if you're differentiable, that means that you're infinitely differentiable, which in turn means that you are analytic. So those words mean the same thing. Holomorphic, differentiable, and analytic, when you get to complex analysis, they all mean the same thing. And that's a little bit confusing as an undergrad the first time that you take it, because you're just like, why do we have these different words? We have words for this already. Like, why are we using different words? Well, when complex analysis was first invented, we didn't know those were the same thing. So we invented new words, and then it turns out they agreed with old words, and now we still use holomorphic. Okay, so holomorphic is what we use, probably just to confuse people, make ourselves feel smarter or something like this, but just something to be aware of, okay? Now, notably, those theorems are obviously not true, right? The differentiable is analytic is C infinity. Those things are not true in real analysis, right? We know that there are lots of differentiable functions that are not C2, right? We know there are twice differentiable functions that are not C2. So differentiable does not imply infinitely differentiable in real analysis, right? And the sad thing is, infinite differentiable also does not imply analytic in real analysis. So I'll give you this example quickly because, I'm not going to work it out. It's just it's a little tedious, but I'll give you the example of an C infinity function that's not analytic. So example, so consider this function. And let's just map R to R, it doesn't matter. We just need some interval containing 0. So e to the -1 over x squared. Which should this be? This is, I think, just strictly greater than 0 and or 0 if x is less than or equal to 0. Okay. So, I'm going to phrase this example as determine the analyticity of f at 0, but the answer is it's not. And I'll outline what you need to do to prove this. So determine if f is analytic at 0. So first of all, it's not entirely obvious that this function is actually C infinity. It is, okay? The limit as x approaches 0 from the right is equal to 0. So first of all, the function is continuous. In fact, if you go into Desmos and you plot it, you'll see that it looks pretty smooth. And you can go through and you can do the math, and it's a little bit complicated. You have to do a couple of tricks to do this, which is why I'm not going to do it, because it actually would probably take us about 20 minutes to do. It's not hard, it's just long. But basically what you can do is you can show that this is C infinity. That's actually a pretty easy proof, okay? Proving that you can differentiate it as many times as you want. So you can show that f is C infinity And without too much trouble, you can show that its derivative, every single derivative at 0 is 0. So this means that its Taylor series at 0 is the 0 series, right? Thus, its Taylor series is x to the power of k. All of these things are 0. So it's literally just all the coefficients are 0. This is the Taylor's, the 0 series. This has an infinite radius of convergence. Right? But notice that there's no open interval on which f of x agrees with its Taylor series, because its Taylor series is 0 everywhere. But f of x is certainly not 0 for any x which is positive, right? Because e to this stuff is never 0. But there's no interval containing 0 on which f agrees with its Taylor series. And you might say, oh, well, it actually does agree to the left, right? It agrees when x is less than 0. So actually, if you want, it makes the proof a little bit harder, but what you can do is instead of over here, if you want, you can just say x not equal to 0 and x equal to 0, and it'll still work. You'll still get that all this function is c infinity, and all of its derivatives at 0 are 0. So it's still not analytic, but this function now definitely doesn't even agree on the left-hand side either, right? Like this function is not 0 everywhere except 0, yet nonetheless its Taylor series is 0. Now this makes the analysis a little bit more complicated if you do this function instead of the one that I've written down for you here. But just so you know that this counterexample can be extended if you're like, well, maybe we just need to take one-sided intervals instead of two-sided intervals, okay? So just as sort of a heads up there, it is easy to break that. Okay, so boom, there you have it. So this is an example of a C infinity non-analytic function. So let's say notes. So 1, this is a C infinity function, which is not analytic. Is not analytic. And again, I'm sort of asking you to take that a little bit on faith. It's actually not easy to construct examples of C infinity non-analytic things. And even this, which is sort of like the canonical example or the quintessential example, it's the example that everybody uses, up to possibly doing that little change that I recommended of doing x not equal to 0 and x equal to 0. This is the example, this is the easiest example of something that we can find, right? So this is something that happens. So it's C infinity, but not analytic. 2, this says that different functions can have the same Taylor series. Can have identical Taylor series, because certainly the 0 function has a Taylor series which is also 0, right? So that kind of sucks, because it would be really nice if every Taylor series sort of uniquely came from a function. But as a general rule, we don't know, right? We can't do that. We can't say anything about that. So this function does, in fact, like I said, its Taylor series is the same as the 0 function. We can't distinguish them. And 3, it'd be really nice if we had some sort of theorem saying like, oh, okay, well, if you've got a function, you can compute its Taylor series. Well, as a power series, it has a radius of convergence, and maybe, it'll agree on its with the original function on its radius of convergence, or on some subinterval of its radius of convergence? And the answer here is no, we don't even get that, because this Taylor series has an infinite radius of convergence, right? It's the zero series, yet it agrees with its original function absolutely nowhere except for 0 itself, right? So the radius of convergence of the series has nothing to do with whether a function is analytic. ROC has nothing to do with analyticity. And that makes us sad, right? Because it'd be really nice if we did know something about that. I guess I should add number 4. There are everywhere C infinity, nowhere analytic functions. Okay, so this is a function that, to the best of our knowledge, just fails to be analytic at a single point. You might say, well, it's kind of pathological there, right? Like maybe that's the exception rather than the rule. No, there are functions that are everywhere smooth, but nowhere analytic. And only real functions, again, right? This doesn't work in complex analysis, but there are functions that are everywhere smooth, nowhere analytic. Now, to my knowledge, the easiest proof of the existence of one of these things requires basically, third, if not fourth year measure theory. So no, because it's only continuous. So like Weierstrass is everywhere continuous, nowhere differentiable. So we sort of immediately lose the C infinity thing that we want. So yeah, I mean, even the simplest proof I know of the existence of an everywhere C infinity, nowhere analytic function requires like, fourth year measure theory in order to prove. And actually it's a statistical proof, believe it or not. It's pretty wild. So these things do exist. Okay, again, they don't exist in C, which is sort of a nice thing here, but they do exist. So make sure that you don't ever make that assumption, right? That there are functions that are mostly analytic or almost everywhere analytic or analytic up to a set of measures 0. That's not true, okay? These things just don't exist. So our life sucks now, right? Like we're in a bad place. We don't know what to do. But, there's still sort of a Chekhovian gun hanging around here, which is, I mentioned the Taylor remainder theorem. And the TRT is the key that we need, to talk about analyticity. So the Taylor remainder theorem is the key to proving analyticity. Okay. And one of the things that we can do here, for example, here, let's just do it. Let's just prove that like sine is analytic. So example. So let's show that sine from R to R is analytic on everywhere. So, right? I mean, like it's actually analytic everywhere. Now, if I recall correctly, this function is actually entire. So what this normally means is that when you're proving analyticity, you just need to prove it for every point, right? What I'm actually going to do is show that effectively, well, I guess I should do it for every point anyway. Okay, so let's do it for every point. So let's say fix some point A in R, right? So we want to show it's analytic, i.e. we want to show that there's some interval around this point A in which the Taylor series actually converges to sine of X. So how do I want to do this? All right, well, let's just write it. Well, there's not much we can really say about the Taylor polynomial at this point, but the important thing that we can say is that because we know something about the derivatives of sine, we're going to be able to bound the remainder, right? So we know that, I should have worked this out ahead of time. So f to the k of x is equal to -1 to the k. Which one do I want to do? Let's do even. So this is going to be sine of x if k is even, right? I guess I should write this as 2k. Right, does that work out? So when k is equal to 1, I get negative sign, and that is the second derivative. When it's equal to 4, yeah, that looks right to me. And then f of 2k plus 1. Let's do 2k minus 1. Here, I'll work it out in a second. -1 to the k cos x. Right, so first derivative would be when k is equal to, oh no, I do want plus 1. So that k is equal to 0 for k and n. Right, so we get this like fourfold periodicity in the signs of our derivatives of sine, right? So sine x goes to cos x, goes to negative sine x, goes to negative cos x, and then we start at the beginning. And the great thing here is that everything's just sine and cosine, so that when we take the absolute value, we always get that it's less than or equal to 1, right? So thus, the absolute value of f to the k of x is less than or equal to 1 for all k and k, or k and n, and x and r. Right? And now we're going to use the Taylor remainder theorem. So thus, by the TRT, the remainder at any given point A, let's say at absolute value. So that's going to be equal to f k c divided by, oh, I guess I'm using n here, so I got to use n plus 1 factorial, x minus a to the n plus 1. That's going to be less than or equal to n plus 1 factorial, right? For all x. So for any n in n and x in R. Now this is by itself actually enough to prove analyticity, but it is actually enough to prove entirety. So for any fixed x, this thing will eventually, like we could take a limit as n goes to infinity, right? And get that this thing actually does converge. But because we're just trying to prove analyticity, let's just choose an interval, right? So let's say the absolute value of x minus a is less than 1. So let's set delta to be equal to 1, so that if x minus a is less than delta, then the Taylor remainder is then less than or equal to 1 over n plus 1 factorial. This is actually independent of x, right? And so this is going to go to, like, we can easily make this 0 in the limit as n goes to infinity. And again, you can epsilon delta that if you want, but it's really not necessary. And since if the remainder goes to 0, that tells us that, yeah, right, the Taylor series and f are in fact equal. So k equals 0 to infinity. Yeah, I'm just going to write it like this because I don't want to write out, well, I guess, nah, yeah, let's just leave it like this. So sine is analytic. Okay. Now, again, sine is actually what we call entire. And you've probably heard me say this, but I'm not going to worry too much about it in defining it. But what entire means is that at any point, when you take its Taylor series, its radius of convergence is actually infinity, and the function actually agrees with it's actually analytic everywhere. So it's not just analytic at every point everywhere, but like has, okay, how do I say this? its power series has an infinite radius of convergence, and the function agrees with its Taylor series on that entire radius of convergence. Does that make sense? So again, when we get to here, we can say, listen, for any fixed x, that thing for sure goes to 0, right? The number in the numerator is just fixed, and then the n+1 factorial goes to 0 really, really quickly. So for any fixed x, this thing actually goes to 0, which means the Taylor series for sine at any point does actually agree with sine at that point, for any point in the real numbers. Does that make sense? i.e. the delta that we can take here is actually infinity for every single point in the real line. Now, again, I'm trying to prove analyticity. I can take delta equals 1 just to make my math work out nicer, but in fact, delta equals infinity will work for every single real number. Do you see that? Do you see that that works? Like if I fix an x, that number that I've highlighted goes to 0 for sure. Is that okay? Anyone freaked out by that? And you can see like a really important thing that happened here that we really don't get with that non-analytic example, if you think about it, is the boundedness of the function and its derivatives, right? It was really, really critical that I could say, listen, every single derivative of this function is less than or equal to 1, right? And that allowed this term right here to vanish. I was able to get rid of that. That's not true with that non-analytic example that I gave you above. Think about it. It's e to the negative 1 over x squared. And when you differentiate that, you're going to get 1 over x e to the negative, or like, I don't know, negative 1 over x cubed e to the negative 1 over x squared sort of thing. And yeah, I mean, that function is sort of, that derivative is nasty. It's ugly. The e to the negative 1 over x squared still dominates. It's still going to force everything to go to 0. But if I recall, if you like graph that thing, it does actually sort of have local maxima that keep getting bigger. So that function is effectively not bounded. So you have to be careful about that. That's sort of the idea there. Because yeah, it's, we couldn't do that in that non-analytic example, but we can do it here. So is everyone okay? Does that make sense? Let me get rid of my highlighting here. Oops. Okay, I'm going to assume that your silence is approval. All right. So basically, there is a theorem here that we can use for analyticity. So theorem. So what do I want to say? So if f maps I to R is C infinity, and there exists M and C greater than 0, such that we can bound this k factorial for all x in I and k in n, then f is analytic. On I. Do we need soup? Yes, you're right. We do need soup. Thank you. So x in I. There we go. Thank you. Okay, so you can see here, we don't even need this theorem is very nice because it doesn't even require that your function is bounded, right? The soups of these things are getting bigger in general, but we're saying that they can only get so big, right? We're sort of like really limiting how quickly they can grow. So let's say we can prove this. I kind of only did my rough work when I was prepping for my lecture here. So let's see if I can't make it a nice proof to begin with. So proof. So again, let's fix some point A. A in our interval, right? So what do we need to show? We need to show there's some delta on which my Taylor series agrees, right? On which my function agrees with my Taylor series. So set delta to be 1 over C, which again, we know is greater than 0 because C is greater than 0, right? We're told that C exists, it's greater than 0, so we're going to let delta be 1 over C. Okay, so we need to show that f of x is equal to the Taylor polynomial, or the Taylor series, when x minus a is less than delta, right? In particular, this is equivalent to showing that the Taylor remainder goes to 0. So equivalently, we need to show that for every x minus a less than delta implies that the limit as n goes to infinity of Rn x is equal to 0. This one we are going to do epsilon delta. Okay, so let's say fix now x such that x minus a is less than delta. And let epsilon greater than 0 be given. Right, again, we just need to do pointwise convergence of these Taylor remainders, right? We don't need to do uniform convergence. So we can fix the x first. We don't care about uniform convergence here. So fix x such that x minus a is less than delta, let epsilon greater than 0 be given, and choose, I'm trying to remember which one I need here. So choose n in n such that I think I want m to be greater than m over epsilon, right? And again, so that's the m from the theorem statement, right? The capital M, that's positive, so that's okay. Epsilon's also positive, so that's also okay, right? So by the Archimedean principle, I can certainly find an n which does this. I'm pretty sure this is the n that works. Let's find out. Okay, so again, I'm trying to show that Rna goes to 0. So let's look at, so thus, if n is greater than or equal to n, we're going to have Rna x minus 0. Now, by the Taylor remainder theorem, this is going to be, oh, I've already used C, didn't I? So now I have to use a different number. Let's use beta. For some beta in, where do I want it? I guess this is in A to, it's in the interval x to a, right? How do I want to write that? Well, let's just write it in words that between x and a, right? Because I don't know which is bigger, so I'm just going to write that because that's what the theorem tells you, right? That beta is actually between x and a. Okay, and now everything is basically fallen into place. So the n plus first derivative of my function at beta is certainly less than or equal to its sup, right? So I'm going to replace that now with m c to the n plus 1 factorial divided by n plus 1 factorial. I also know x minus a is less than delta. Delta is equal to c, right? So this is going to give me c, 1 over c to the n plus 1. What do I want here? Where does my epsilon go? Epsilon. Oh, yeah. Okay. Where did that go? I might need to be trickier than that. Maybe I need x minus a to be less than. All right, how do I fix this? It shouldn't be too bad, right? So I think I just need to change delta actually. No, I can't. So because that's going to choose there. C, x minus a is less than delta. It's going to be c to the n plus 1 there. Drat. Everything is just going to cancel out, right? It's just going to give me the c. What did I miss here? Or rather, it's just going to give me m because everything else is going to cancel out. I might just need to change the theorem. What did I screw up here? I bungled up something. There's an easy fix, but I don't know if I want to do it. The easy fix is just to change the theorem, right? Yeah, and I'm trying to think about where to do it. So I can't put epsilon in here, right? But I could put m in here somehow. But then I don't know much about m and c, so that doesn't do me any good. I really want all the m's and c's to disappear and just be left with some n's. So I think what I'm going to have to do, everyone, let me do this for now, and then I'll think on this and see if I can fix it. So what I'm going to do is I'm up here. Okay, I'm back up in the theorem statement. I'm just going to cheat because I'm a cheater, and I'm just going to write k minus 1 factorial because I'm a cheater. And then I'll try and figure out how to fix this later because I seemingly forgot. So now this is just n. And there we go. Now it's fixed. Okay. So again, this is a slight weakening of this theorem. I might have actually made a typo, and maybe it is supposed to be k minus 1 factorial. But if you see the fix, yell at me. Anyway, if I implement this, then what this is going to do, what this is going to change down here. Zoom in. What are you doing? Okay. Then this will now become equals m over n plus 1. Right? And I guess maybe I should do, yeah. Right, so now this will be less than epsilon because of this thing. Because I've chosen n to be strictly bigger than that. And then I guess I should maybe do like minus 1 or something. And now I've got less than epsilon, which is what I wanted. Okay, so I feel like that should work for just k factorial. And I'm, my brain is just not working for some reason. This is why you don't just do the rough work, everyone. When you are prepping a lecture, you should actually write the damn thing up. But yeah, I seem to recall that being k, so I must have missed something subtle, which I can do that I just wasn't thinking about. Oh yeah, that could work. Ooh, good one, Alex. Yeah, good job. I think that would work because then we'll just get 2 to the n. Yeah, that's a nice one. That's a good fix. I like it. I like it a lot. So let's put the n plus 1 factorial back in here. Let's change this maybe back to k factorial. And then so this will become now 1 over 2c, right? This will become m over 2 to the n plus 1. Yeah, okay, so then we just need to change this, right? So we just need to such that n is what? Well, n is such that this thing is less than epsilon. right? Choose n in n such that, 1/2 to the n plus 1 is less than epsilon over m, or something like that. I guess we could just put the m over here. We don't need to mess around with that. Yeah, good thinking. Okay, and that'll fix it. Very nice, good catch, good catch. Okay, so that's sort of how we take care of that, which is nice. So again, sort of Taylor remainder theorem being the critical thing here that allows us to do analyticity, right? To make sure that our functions are actually analytic. And again, we don't even need boundedness. Like when we did it with sine, that was a little bit powerful. I forgot the power on one of our, yeah, right, thank you. And so, yeah, the Taylor remainder theorem is very nice. If your derivative is bounded, even better. But again, sort of the power of the theorem is you don't even need boundedness, right? You can just, you're done. If you get some sort of nice bound here, right? Like this, again, this bound here is growing, but that's okay. It's allowed to grow as long as it doesn't grow too quickly, right? So that's nice. Okay. Now let's see, I guess there's sort of like one more theorem, and then I'll give you a quick and dirty example. There's lots of things that Taylor series are actually really useful for. There's one more theorem I want to do, or I guess there's actually two more theorems. So theorem, so if the sum from ck x minus a to the k, so what happens if we try now, remember, so I said last time we started with the series, then we defined a function, this time we defined a function and went to a series. What if we go in a big loop, right? So what if we start with a series, define a function, and then take its Taylor series? So what if we do this big loop? What happens? So if this is a power series with radius of convergence some r, and f is defined in its usual way, right? Like a minus r to a plus r to r, x maps to the series. Then the Taylor series for f at a is itself. And therefore f is analytic at a. I guess say f is analytic if r is positive. Is analytic at a if r is greater than 0. Right? So if you have a power series to begin with, use it to define a function, then take its Taylor series again. Well, the Taylor series is the power series. They both agree, and they end up being the same thing. And therefore, if you had a non-zero radius of convergence, then in fact you are analytic, right? This function is analytic. Because obviously it agrees with its Taylor series, because it is its Taylor series, right? Proof of this is trivial. So I'm going to say here, easy exercise. And I say easy because it is easy. All you have to do is check that it is its own Taylor series, right? And so the way that you check that it's Taylor series is compute what its derivatives are. But we know how to differentiate, right? From our conversation last week, we know that if you define a function in terms of its power series, in terms of a power series, then the derivative of that function is its differentiated power series, right? So it behaves exactly the way you want. And so if you go and you actually compute what the kth derivative of this function is at the point A, you'll see you get exactly it back out, right? Like everything just magically works out and cancels out in such a way to give you back the Taylor series. Okay, so it's a fairly straightforward exercise. All you have to do is compute the derivatives and check itself. Now, this is very nice because what it also means is that, what do I want to say here? That if f is analytic at a, so sort of this sets up the following corollary. So if F is, well, let's give F a name. So if F maps I to R is analytic. And so remember now, analytic also implies C infinity, right? Because you have to be C infinity to even talk about analyticity. So if F is analytic, then F prime and its integral, I guess I should say, is analytic at A. Can I just move this over? Then F prime and the integral are both also analytic at A. And their Taylor series are what you expect them to be. K equals 1 to infinity. K F, what do I want? Do I want K plus 1 here? Well, here, let's put this in here, and then we'll figure that out in a second. X minus A to the K plus 1. Yeah, because that's just a constant, right? And then the integral, somebody double check that for me. It's going to be integral from K equals 0 to infinity FKA all over K plus 1, X minus A to the K plus 1. Right? Because that's the CK, right? And the kth derivative at A is the CK. Oh, I guess, no, I need over K minus 1 factorial, I guess. And then this should be K minus 1. There we go. That makes more sense. Okay, and the corollary is, according to the previous theorem, once you know that a function agrees with its Taylor series there, right? Within that radius of convergence, you know that the differentiated and the integrated power series also agree. So you get analyticity, you're done, right? Like you get those things for free. So that's why it's a corollary. So proof follows from the theorem. Right? Because F agrees with its Taylor series, therefore it is a power series. And the theorems from last week about differentiating and integrating a power series, it being differentiable, it being integrable, and the Taylor series agreeing, all those things are still true, right? So we're good. And again, analyticity follows immediately for the same reason. So, okay, that's fine, whatever. We've gotten these sort of theorems out of the way. Why do we care, right? Why do we care about Taylor series? So I've already sort of mentioned you can use Taylor polynomials to do some sort of approximations, right? Like if you're actually trying to write a program to approximate sine of 7, right? Because that's a weird number. So if you're trying to approximate sine of 7, you would use what? Probably 2 pi, because that's the nearest number. So you can actually use Taylor polynomials to do this. But more importantly, Taylor polynomials also show up when you're solving ODEs. So there's lots of times when you've got an ordinary differential equation and you actually can't find a nice expression for your answer, then what you can do is you can just say, suppose that it has a Taylor series expansion, and then just solve for the coefficients. So that's totally a thing that you can do. So that, if you go and you take an ODEs course, you might do that. What else? There are a couple of places it shows up. Oh, there's a thing you can do with limits. I guess I should give you the limits thing. So, do I have one? Let me just pull one out of my book. You remember when I was saying at the beginning of the year that L'Hopital would become stupid by the end of the course, that we would never do L'Hopital again? This is it. So let me just pull up an example. Sure, that's sort of like a board. No, yeah, let's do that one. So why can we use Taylor series? So applications. So here, let me just make one up. So example, and by make one up, I mean steal from the book that I wrote. So the limit as x approaches 0. So e to the x minus 1 minus x squared over 2 divided by sine x minus x. Okay. So when mathematicians do limits like this, any limit that requires L'Hopital, we never use L'Hopital, ever. Okay. What a mathematician does is they compute the Taylor series expansion of these things when it's nice enough, right? There are times when L'Hopital might make sense, but when it's nice enough, we compute the Taylor series expansion of these things. And that's all you have to do is once you know what the series is, you're done. So let me show you what I mean here. What you'll notice is that the top and bottom both kind of look like, a function minus its Taylor polynomial, right? In particular, that means that both of these things, both the numerator and the denominator, look like Taylor remainders. So let's sort of use that in order to figure stuff out. So solution. So note that e to the x is equal to 1 plus x squared over 2 plus x cubed over 6 plus order x to the 4, right? Because this is its Taylor series expansion. And again, we haven't proven it, but e to the x is not only analytic, again, it's entire, okay? This Taylor series actually agrees with e to the x everywhere. Okay, so we get that e to the x is equal to this. Sine x, same sort of story. So sine x is equal to what? So it's going to be equal to x minus x cubed over 6 plus something in x to the 5. Okay, now you guys might not know what that big O means unless you've maybe sort of done some computer science. Big O is how we mathematically are very lazy and say there are more terms here, but we don't care about them. And what you do is you keep track of, because we're taking a limit as x approaches 0, we're sort of keeping track of the biggest term as x approaches 0, the thing that's going to introduce the most error, right? Because the higher your exponential, right? If I've got x to the power of 10, it's going to go to 0 much faster than x to the power of 4. So I'm not worried about that in e to the x, right? I'm sort of worried about the thing that's going to 0 slowest because it's the thing that's going to give me the most trouble. So this big O notation is just what you sort of use to keep track of things. Anyway, as a mathematician, you kind of even ignore that part. You're really not worried about it. And what I do is when I'm computing this limit, so we've got the limit as x goes to 0. And what you notice is that numerator is the difference of everything in this box, right? So that's going to be, here, maybe let me write it out again. And you can do this with everything. You don't just have to do this with limits, but I'm doing this limit in particular because I'll tell you, try and do it using L'Hopital. See how many times you have to do it. So this is going to be what? X cubed over 6 plus the order of x to the power of 4. Sine x over x, that's going to be negative x cubed over 6 plus x to the 5. And then by our sort of like usual trick where we multiply and divide by x cubed, limit as x approaches 0, 1/6 plus x divided by negative 1/6 plus x squared, right? So again, I've sort of divided everything by x cubed. The remainder in the numerator, I know at least it has x, right? Everything in it has a term of x, which I could factor out of everything, but it's got some x's, some x squared, some x cubes. Same thing in the denominator, everything there has at least an x squared term, maybe an x cubed, we know not actually, but an x cubed, x to the 4, x to the 5, x to the 6. So as x goes to 0, those terms all go to 0, and I just get 1/6 over negative 1/6, which is negative 1. And a mathematician would just do this in their head. Right? Because a mathematician really isn't going to do all of this stuff. What a mathematician is just going to do is in their head compute and say, oh, okay, I look at this numerator here and I say, well, sorry, that should be x squared over 2. Say, okay, if I've subtracted the x squared term from that numerator, then the next term, which is going to survive, is going to be the x cubed term. So what's the coefficient of the x cubed term? Oh, it's 1/6. Okay. I look at the denominator, I say sine x minus x. Okay. So what's the next term? Well, x cubed. Okay. What's the coefficient of x cubed? Oh, it's -1/6. Boom. The answer is 1/6 over -1/6. Do you know what I mean? Like, you just, as a mathematician, you're just looking for what those coefficients of x cubed are in your head. You divide them and you can get your answer. So that's how a mathematician would do this problem. If you're to do this problem using L'Hopital, how many times do you think you'd have to apply it? Anyone got a guess? Right? Like, you can sort of see it in your head what's going to happen. Yeah, it's either 2 or 3 times, right? So if I do it once, what do I get? I get e to the x minus 1 minus, x, just minus x. If I do it again, I'm going to get e to the x minus 1, and then I do it again. So I guess that's 3 times. Yeah. So you have to do it. Basically, what it ends up being is you have to do it a number of times equal to the first non-trivial coefficient. Do you know what I mean? So here, notice that we had the x cubed. That's how many times you're going to have to do L'Hopital. So what I mean by this, do you remember when in the beginning of the year when we were sort of talking about L'Hopital, and I said I can make L'Hopital problems that require you to use an arbitrary number of L'Hopital? Like, I can make it so you could have to apply L'Hopital 10 times, because that's easy for me, because I know what the 10th coefficient of e to the x is, and I know what the 10th coefficient of sine x is. So for me, being able to make a problem where you have to do 10 Taylor polynomials, or 10 L'Hopital rules, sorry, is trivial. It's super, super easy, right? So this is why we don't use L'Hopital, right? No mathematician would ever use L'Hopital. You would just use a series approximation for this. Does that make sense? Does everyone sort of see how this would work? And 90% of the time, this is only going to work as you approach 0, because those are the only ones we have the Taylor polynomials for memorized. But in theory, if you're approaching x, if x is approaching 1, you could take a Taylor polynomial approximation at x equals 1. Still probably better than L'Hopital to some extent. But I mean, you got to compute derivatives anyway, but whatever it is. Okay, does that make sense? Kinda. Okay, the last one I'm going to do, because I'm going to let your other courses teach you about why Taylor series might be important. The last one I'm going to do is Euler's formula, just because I think I promised you I would do it. Sure, yeah. I mean, so the physicists will use Taylor polynomials a ton to approximate things, right? Like, you'll see all the time this approximation in physics, for example, like 1 plus x. Right, like you can compute what this thing is, and it's like 1 plus x over 2, for example. And that's basically a Taylor polynomial approximation to root 1 plus x. That one gets used all the time, for example, right, in physics. So these sorts of approximations, and that's probably what you mean for like special relativity, is when you're doing like the Lorentz factor. The Lorentz factor is often approximated because it does look exactly like this. It's got a root 1 plus stuff in it. Yeah, exactly, right? So all of this sort of stuff sort of shows up. Like the physicists will use these sorts of approximations all the time. And it feels sort of dirty. Like, if you ever go and you take a physics class and then they're like, okay, now we're going to take the second, or they'll take the first order approximation. You know what I mean? They're like, we're going to take the first order approximation. We're like, no, why can you do that? I remember the first time I had to do this in a test, and I felt so dirty. So it was actually in a general relativity test, and I had to use the small angle approximation of sine. Do you guys know what the small angle approximation is? Has anyone done enough physics? You probably learned it in high school if you did physics. No? Exactly, sine x equals x, right? So I remember we were doing a test, and it was in GR, and I get the sine x term, and I'm like, I can't do anything with this. And as a mathematician, you'd be like, okay, well, I'm done. I can't do anything. But it was a physics class. So I'm like, all right, I don't want to do this, but I'm going to. So I say, sure, yeah, absolutely, yeah. And so I said, all right, we're going to make a small angle approximation because it was a small angle. We knew it would be. So I wrote, let sine x be, approximately equal to x, and then went through and did the rest of the math. And I got the question correct. And I was like, oh, this is, yeah, I was not super happy with that. But again, it is what it is, right? What are you going to do? Okay, so what I'm about to do here is the last thing we're going to do. And it's a little, that's why we haven't broken yet. Or taking a break, but there's a bit of blasphemy here. Okay, so I'm going to explain a couple things, but I'm going to start plugging complex numbers into our Taylor series, which we don't know that we can do, right? So we're going to, again, you're going to have to take a little bit of a leap of faith here and assume that we can actually do that. But we can. So the Taylor polynomial for e to the x, right, is the sum from k equals 0 to infinity x to the k over k factorial, right? This is the Taylor series for this thing. Again, it actually has a radius of convergence equal to infinity, and it's everywhere analytic. So this actually, it's not just analytic at every point. This series actually converges everywhere to e to the x. And then we've got sine x, which we'll note looks surprisingly very close to this. Right? In fact, maybe let me write a couple of terms here out. 1 plus x cubed over, no. 2 comes after 1 over 3 factorial plus x to the 4 over 4 factorial, 5 factorial plus dot, dot, dot. Okay? This one is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial plus dot, dot, dot. And then cos x is all the even terms, right? To infinity, -1 to the k, x to the 2k all over 2k factorial, right? So that's going to be 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial plus dot, dot, dot. So what we notice is e to the x, sine x, and cos x are really, really close to each other, right? Like it almost seems like if I added up sine and cos x, I would almost get e to the x. Sort of the annoying thing here that's giving me trouble are these signs, right? The fact that there's a minus sign here and a minus sign here. So the fact that sine and cosine seem to be alternating signs is the thing which is preventing me from just saying e to the x is cos x plus sine x, right? If I add cos and sine, I get all the terms, even and odd. The problem is that they're alternating in sign. And there's sort of no way to fix this using just real numbers. But you can fix it if you're a dirty cheat and you use complex numbers. So if I plug e to the ix, right, into this, I get the sum from k equals 0 to infinity, ix to the power of k all over k factorial. And if you remember, so I has that fourfold periodicity, right? So I to the power of 1 is I squared is -1, I cubed is -I, and I to the power of 4 is 1, right? Maybe let me just write that out. So we've got maybe let's do I to the 0 is 1, I to the 1 is I squared is -1, I cubed is -I. And in fact, that should look like almost the derivatives of sine and cosine, right? Which they sort of do the same thing. They have this fourfold periodicity and negate themselves after a certain amount of time, right? Like they sort of exhibit the same behavior. And so if I write out e to the ix, what I'm going to do is I'm going to break this into, basically I want to break it into its even powers of I and the odd powers of I, because the even powers of I are just real numbers. They're either plus or minus 1. The odd powers of I are imaginary, purely imaginary. They're either plus or minus I, right? So I'm going to break this into its even and odd powers. So I'm going to get ix to the 2. So let's do the even first. X to the 2k over 2k factorial plus the sum. Here, let me move this over. k equals 0 to infinity, ix to the 2k plus 1, x to the 2k plus 1, 2k plus 1 factorial. Okay, so I said I to the 2k, right? So those are going to be the real numbers, but they're just going to alternate with plus or minus 1 signs. Oh, sorry, I've already written. I don't know why I wrote that again, right? Because I've got the ix in there. Here, maybe let me write this as like I to the 2k, x to the 2k like that. I to the 2k plus 1, x to the 2k plus 1. There we go. I think maybe that reads a little bit nicer. Sum from k equals 0 to infinity. Okay, so I'm going to get -1 to the ki, x to the 2k plus 1, all over 2k plus 1 factorial. And if I pulled this I here out, right, I get exactly which is a formula I think some of you have probably seen before, right? Especially, I think if you've taken, at the very least, if you went and took 223, they did it. I don't know if you would have talked about this in 240, but this formula of e to the ix being cosine plus I sine. So is this, have you guys seen this before? Like maybe you've learned of this before, but have you learned like why it's true and using Taylor series in order to do it? Does that look familiar? Okay, well then, yeah. So if you haven't seen this before, now you have seen it. So here's the relationship between e to the x and cosine x and sine x. And again, this should be crazy, right? This is very surprising. The exponential on the surface of things is not in any way related to sine and cosine yet, right? But by the magic of Taylor polynomials, we now get that, no, in fact, they are the same thing, right? And by the same thing, I mean, they are really the same thing. Look, the exponential is cosine plus I sine. That means that we can do a couple of things, right? So this means that sine of x is what? So it's going to be e to the ix. Do I want, I think, minus e to the ix? Here, I'll double check my signs here in a second. Of course, you can also do it. Right? Okay, so cos is, oh, sorry, it should be negative ix. So cosine is even, so that's not going to do anything. So coses will kill each other. So I get I sine minus negative I sine. So that'll be 2I sine divided by 2I. So yeah, my signs there are correct. All right. So I can write sine in terms of the exponentials. And I can write the exponential in terms of sine and cosine. So now these are the same thing. And for those of you who have learned about hyperbolic, oh, sorry, not 2I over here. For those of you who have learned about hyperbolic cosine and hyperbolic sine, you might wonder, like, why are those things defined the way they are? Notice that these are basically the definitions of hyperbolic sine and hyperbolic cosine, but without the exponentials, right? And so what this actually gives you is the following. So we get, for example, that cos x is cos ix, and we get that sinh x, or I guess sine x, is equal to, what do I want here? So I guess it would just be I hyperbolic sine ix. Right? So that's why hyperbolic sine and hyperbolic cosine are defined the way they are, is they're actually, oh, sorry, shouldn't be a sinh over here. Is that if you go and you throw in the imaginary numbers into the hyperbolic sine and hyperbolic cosine, you do actually just get out sine and cosine, right? So that's actually the reason why those two things are related. Another thing that you might be able to do, does anyone know what the modulus of e to the ix is? Like as a complex number, what is the modulus of e to the ix for any x? Sure, yeah, it's equal to 1, right? And in fact, you can just check that because what's the modulus? Look at this. You remember how you can write every complex number as a plus ib? Notice that this is exactly a plus ib, right? So then the modulus is the square root of the squares of these things is equal to 1, right? And in particular, that tells you that e to the ix, as x goes from 0 to 2 pi, is just the unit circle. Right? The modulus is the set of things. So if you identify the complex plane with R2, e to the ix has norm 1, so it must lie on the unit circle. But more importantly, like again, we know that there is this identification of the complex plane with R2. Yeah, what are the things in the unit circle look like? Well, they have coordinates, cosine, and sine, right? So that means that the unit circle is precisely e to the ix, as x is allowed to go from 0 to 2 pi. Right? Does that make sense? And then this results in Euler's formula, right? Because then e to the I pi is equal to what? So it's going to be cosine pi plus I sine pi. That's equal to -1. So that implies that e to the I pi plus 1 is equal to 0. Right? And the reason, I don't know, again, so I'm certain that many of you have seen this, but the reason why this is profound is because these are the 5 fundamental constants, right? E, I, pi, 1, and 0. These are the 5 fundamental constants. Ostensibly, they really aren't necessarily related to one another, but here's a formula that involves all of them. So e to the I pi plus 1 is 0. And that's why, mathematicians love this formula, because it's crazy. It's absolutely crazy that this is true. Okay? Does that make sense? So now, if you haven't seen this before of like why e to the ix is cos x was some, oh, here's a fun thing I forgot to mention. What do I want to say? I might have told you this before, but I can't remember if I did. Does anyone remember what the radius of convergence is for arctan? So here's maybe a side thing. So if I take, what do I want to say? So the sum from k. So if I look at this power series, we know that's equal to 1 over 1 minus x, right? Right, okay. Though not including plus or minus 1, right? Because it doesn't converge for the geometric series. Oh yeah, you were saying for arctan. Okay, so now an important point here is that this function is not defined at 1, right? 1 over 1 minus x is not defined at 1. So if you think about this, if I say the radius of convergence here is limited by the asymptote at x equals 1. Do you all agree? So basically, this thing wants to be bigger than it is, right? It wants to expand out. It wants to be, the radius of convergence wants to be as big as it can. We're centering this power series at 0. But when we write out what this expression is, we actually run into this obstacle at 1. We get a vertical asymptote at 1. And it's relatively easy to fix this if you were to actually take, a power series for this geometric series at the point, say, what do I want to say here? No, that would be a half. Yeah. So now, here, let's change this up a bit. So what if I did x over 5 to the power of k, right? That's going to be 1 over 1 minus x to the power of 5. That's going to be 5 over 5 minus x, right? If you had to guess, what do you think the radius of convergence is for this thing? In fact, you can just see it if you know what the answer is. But what is the radius of convergence for this power series? Anyone? Yeah, it's 5, right? And you can see that in two ways. One is here. For this is still a geometric series to converge. So for this to converge, it will converge if and only if this is less than 1, right? And of course, you can just multiply both sides by 5, and then you get your radius of convergence is 5. But again, you can also see it from here. It wants to be as big as it can, right? The radius of convergence, it's stretching out, stretching out, stretching out until it hits something where you divide by 0. And then it says, oh, okay, I can't go any further. And this turns out to be true in general. Okay, most functions, when you compute, or if you start with a power series and you want to compute its radius of convergence, the radius of convergence is going to stretch and stretch and stretch and stretch as far as it possibly can. And once it hits a point where it divides by 0, that's basically the boundary of your radius of convergence. That's why functions like e to the x, sine x, cos x, the Taylor series for these things have an infinite radius of convergence because these things never divide by 0, right? So their radii of convergence can stretch out to infinity. Now, as sort of pointed out, this doesn't seem to be universally true because arctan also has a radius of convergence of 1, but arctan doesn't really divide by 0 at any point, right? There are obviously some sort of, well, I mean, it kind of does, right? Like if you think about arctan, maybe I can think of another, maybe a nicer one here. But yeah, arctan actually does have some asymptotes in it, but let me see if I can find another one. 1 over 1 plus x squared. Okay. So again, you look at this thing, no issue, right? Defined for every real number, has no vertical asymptotes. Everyone agrees? Right? 1 over 1 plus x squared. Never, you'll never divide by 0 here because the denominator is always greater than or equal to -1. Nonetheless, has a radius of convergence. If you were to write this thing as this geometric series, also has ROC equal to 1. Okay, right? Because x squared is less than 1 if and only if x is less than 1. So it seems like I'm a liar, right? Seems like I'm lying because this thing doesn't have any vertical asymptote. So why would its radius of convergence be limited to 1? But it does have a vertical asymptote. Where is its vertical asymptote? Which is a little bit of a trick question, but can anyone tell me, where is it? Exactly. Yeah, its vertical asymptote is at I, and plus and minus I, right? And what is the distance from 0 to plus or minus I? Exactly. Right? So what this says is that the real power series can detect its complex poles, right? Real power series are able to, again, they're still stretching out. They're stretching out as far as they possibly can in order to converge, and are going to stop only when they hit, when you get when you divide by 0. But the crazy thing is that even though this is a real function, its radius of convergence is limited by its complex pole, by where you would divide by 0 in the complex numbers, right? That's a super cool thing, I think, because there's no reason to expect that that would be true, right? Why would that be true? How is this entirely real function? We've done nothing here to talk about complex numbers, right? Nothing whatsoever. And yet it can detect its complex poles, right? And again, a pole is just where you divide by 0. It can detect its complex poles. How? How is it doing that, right? Crazy, 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 crazy that should be true. And generically, that's true, right? Functions, their radius of convergence, if you get something that doesn't have an infinite radius of convergence, it's because it has either a vertical asymptote that you can see, or its complex version has a vertical asymptote that you can't see. So same sort of thing happens there. Ends up being very, very surprising. Okay. Anyway, that's it for Taylor series. I think we're done. Right. Now, that being said, Taylor series, we're not going to use them at all in your final exam. They're not going to show up at all anywhere because your final exam is 100% new material. So don't worry too much about this material. I think it's fun. I think it's interesting. You know, learn it. Done means all done. That's right. Done means all done this time. We are completely done. MAT157. I mean, you know, modulo your final exam. But we have finished the material. There will be no new material. So Thursday's lecture is canceled. I'll show up if anyone wants. So, but it'll just be office hours. But then again, there isn't really much to ask about because your final exam is new material. So there's really no point studying for your final. And that's it. Tutorials will still run. Yeah, tutorials will run as usual. They're gonna, you know, cover some of the stuff if you want to learn it a little bit better, but everything is normal. But like I said, I will be there Thursday at 9 a.m. if anyone wants to come and hang out. But if nobody shows up in like the first 10 minutes, I'm going to leave. But don't feel any pressure to show up, because if I, you know, get to shut off the Zoom meeting and go take a nap or something, I won't be upset. But yeah, that finishes it, everyone. So you should give give yourself a pat on the back that you've successfully, you know, managed to struggle through and get to here. It's not quite done. You still have an exam, final exam. But like I said, I think the final exam will be fun. I think you'll all really enjoy it. Yeah. Other than that, I don't think there's too much to say. It's been a fun year. I kind of wish we had an opportunity to do this in person. It's kind of too bad that, you know, we were online all year, but it was still fun. I really enjoyed it. It was great having you all as students, because man, you guys are, yeah, you're some good students. You asked some great questions. We had some good times. I had a good time. Hopefully I'll see a bunch of you in 257. If you see me around campus next year, definitely come say hi. Exactly, in 257. I'm hoping I see a bunch of you there. Make sure you come say hi to me though if you see me on campus. But that being said, make sure you tell me who you are, right? Most of you did not turn your cameras on, so I know your names, but I have no idea what you look like. And if I have no idea what you look like, then, you know, because you know what I look like and you know my name. So you see me on campus, you can be like, oh, hi, you know, Tyler, how are you doing? And I'm like, I have no idea who you are. So, you know, I don't know what your faces look like because you didn't turn your cameras on. So just make sure that when you see me, you tell me who you are. And usually this is funny because it's backwards than most years. Most years I know what everyone looks like and have no idea what anyone's name is. This year is completely the opposite direction, right? I know what everyone's names are, but I don't know anyone's faces. Okay. Yeah, but like I said, no, it was a good time. I really enjoyed it. Yeah, no, that's true. That's true. And I'm still running Queen's Park, right? So if you like, and I'm out there for like Monday, Wednesday, Friday are my run days. That might change once classes end, and I'm usually out there for like an hour and a half, 2 hours. So chances are you'll see me if you're out there. I don't know. It's usually somewhere between 9 and 12. Bring your running stuff. We'll just do the 157 run group. I think that would be hilarious, but that's right. You're all much younger than me, so you should all be able to outrun me. That's what I expect. But you're also all math nerds, so maybe not. It's hard to say. exercise is great for the mind. It makes a big difference. When you're feeling stressed out, when you're feeling like, especially when you get like some sort of writer's block or roadblock in terms of solving questions, man, go out there, get running, or just some sort of other exercise, right? It doesn't matter what it is. Even if it's just a walk, walking is phenomenal, right? Clears the brain. It's just, you really all, I think, you should try and find something that isn't mentally intensive, because you're all doing mentally intensive studies. If you get an opportunity to go out there and just sort of like turn the brain off and just, exercise out that anxiety and that stress, makes a huge difference in terms of your ability to think, to problem solve, to sleep, to, live sort of a stress-free life. And again, it doesn't need to be intense. Legitimately just go for a walk. And walking is phenomenal. Put in some music, put in a podcast or something, go for a 30-minute, hour-long walk. And, that sort of stuff is really critical to making sure that you don't lose your mind. So make sure that you can do that if you can. I used to skate a lot, right? Like UTM is probably not great for that, but if you're downtown, you get an opportunity, you guys get to go to Varsity Arena for free. So skating is a ton of fun if you get a chance to do that. But yeah. Okay. Now I'll still be around by Piazza and email, so you can still get a hold of me those ways, including during the test. So once the test goes live, you guys really shouldn't talk to each other about the test. I can't prevent you from talking to each other, but try to avoid talking about the test. You can talk. I will, just like our term test, I will set Piazza to private, and you can send me messages on Piazza, or you can do it on Discord if you're on Discord, or you can do it by email. Yeah, and I'll sort of announce something here probably on Friday, giving you a little bit more details, but again, it's a take-home exam. You'll have like 10, 11 days, however long to do it. So, you'll figure stuff out on the fly as well. Anyone got any questions? Anything else there? I don't know. I really don't know. Because again, so it's going to depend on you. So the due date is the same date as our regularly scheduled thing. Do you know what I mean? Like when was the regularly scheduled exam? It was the 21st at 8 p.m. I think was when we were supposed to write our exam on Friday, April 21st from 5 to 8 p.m., right? So that means that your exam is due at 8 p.m. on April 21st. The format, right? The reason why it's impossible to tell how long it would take you to write is because the format is going, like every person is going to be different. There's like 30 questions and you get to choose which questions you do, right? Like you don't have to do them all. You can do a bunch of them. You can do a few of them. So it's going to depend on sort of what you want to do and how many, there might very well be times when you start doing a question because you think you can do it. And you're like, no, I don't think I can do this question anymore. And you go to another one. And if you do that a bunch of times, it could take you a long time to write. But alternatively, you could might pick out a couple of questions, get them right away. And then, it takes you almost no time. I will put it up. So it'll be up on the first day of exams. So it'll be up on the 11th. I'll probably put it up by around noon or so. I'll make a definitive call by Friday. And then on Friday, I'll post an announcement giving more information about it. How many hours each day? I don't have a good recommendation for that. I do recommend, though, just sort of like our take-home tests. My recommendation would be as soon as it goes live, give it a good, thorough reading. You know what I mean? And just sort of like sit down with it, maybe spend half an hour just sort of thinking about it, maybe writing some notes, print it out or something, write some notes on it, and just get your brain sort of working on it in the background. You know what I mean? If you've got a bunch of exams, it's going to depend on your exam schedule too. If you got like 3 exams in a row, you probably shouldn't think about it at all in that time period. But you should probably take a look at it as soon as it comes out, just again, so you have a feeling for what it's asking, for what the questions might be. Maybe pick a couple of questions, study them in the sense that you really understand what they are asking. That way, again, you should be very surprised at how good your brain is at working in things in the background. But it can't do that, right, if you don't know what the question is. So spend some time, read the exam, make sure you understand what it's asking, let your brain work on some questions in the background, have a piece of paper beside you at all times, because you never know when you'll just be doing something else and suddenly your brain will be like, hey, this is how you solve that problem. And you need to be like, oh man, I got to write that down. Right. So yeah, exactly. Yeah. You read those questions the first day, they stay in your mind, and like, yeah, you solve them. Sometimes you'll wake up in the middle of the night and you'll be like, oh, I know how to solve that problem now. Right. That totally happens to me, where I wake up in the middle of the night and I either forgot something or I figured something out, and I'm just like, oh yeah, okay, that's how I somehow did it in my sleep. But again, you can't do that if you didn't read them, right? So read them, don't leave it until the last minute. The test isn't hard, right? And it really is as hard as you want it to be. So there's lots of easy questions, there's lots of intermediate questions, there's lots of hard questions, and you get to pick which ones you do. And it's perfectly, you can get 100% by doing easy questions, but you have to do a lot of them. That's sort of the way that goes. You get 100% by doing all hard questions, and you don't have to do nearly as many because they're hard, right? So every question has a certain point value. You can do 110 points worth of questions. The test is marked out of 100, so you can get 110% on the final exam. And it's up to you which questions you do. There are 2 mandatory questions that you have to do, that everyone in the class has to do. And then after that, you get to pick, and you can do whichever questions you like, right? And there's 30 of them. So I think most students will choose like 10 or so. It usually is about, I think the median is about 10 questions that students will do. And again, there's a combination of like really easy ones that students know they can just grind off, no problem. And a couple of intermediates, a couple students will try the harder ones. So yeah, it's impossible to say how long it'll take, right? Just work on it a little bit when you get some time, and then don't stress about it too much, but maybe set some time aside where you take it seriously, right? Where you're like, okay, I'm really going to work. Yeah, you can 110% on the exam, for sure. The exam itself will have more instructions on it, but yeah, you can choose 110 points worth of problems to do. If you do any more than that, I will ignore the rest that you do. But I will mark your first 110 points worth of problems, but the exam is out of 100. So you can get 110 out of 100. No, because students who attempt questions don't submit them if they don't complete them, right? So I don't have any idea what usually that is. Difficulty of questions attempted. Again, there's typically a good sort of smattering, in the sense that a lot of the students will take many of the easier ones because they're just easy grades. There's almost always a couple. First of all, you can't do the entire test just doing easy questions because there just aren't enough of those questions. You're going to have to do a couple of intermediates. There are a couple of hard ones that are definitely like not that hard, right? Like they're ranked as hard questions, but they're not really that hard. And then there are a couple of hard ones that are really hard. So in my experience, most students sort of independently find a core group. Like again, if the average student does like 10 problems, there's like 8 problems that every student does. And then those last 2 sort of vary by individual, and they will choose sort of different, every person will choose those last 2 questions to be different depending on their taste. But then most students seem to narrow in on those core 8 questions or so that they are confident that they can answer pretty well. So, but yeah, I don't have much in the way of stats. Grades are pretty solid though, as a general rule. Again, it's the sort of thing that like if you put any effort into it whatsoever, you should get a good grade. The questions are not generally difficult. Okay, anyone else? All right. Yeah, sounds good. I think we can call it there. Absolutely. Thanks, everyone. I had a great year. I really enjoyed teaching you all. I hope you enjoyed being had. Yeah, and I'll see you around, hopefully. Any anime recommendations? No, not really. Thanks, Mahmood. Yeah, thanks so much, everyone. Hopefully I'll see you in 257. Have a good summer. Have a good exam. Have lots of good exams. And I'll see you around.